Okay, I'm Sungyu Lee, PhD candidate. I continue lecture about underwater acoustics. Our contents is like this. I will explain about speed of sound and sound propagation in the ocean, and I will introduce some application of acoustics. So at first, here is a question about speed of sound. Speed of sound is can calculate by Newton-Laplace equation. Is square root of differential pressure divided by differential density, and also can calculate as square root of Burke modulus divided by density. Here, Burke modulus means kind of stiffness. Speed of sound increases with the stiffness of the medium and decreases with the density. And speed of sound is water depends on the temperature and pressure and salinity. Some researchers present empirical formulas like this: is C is speed of sound, T is temperature, degree of Celsius, and S is salinity, T is depth. So we can calculate some speed of sound, and you can also observe that when higher speed, higher salinity, higher speed, and more deeper depth, higher speed and speed. But it is empirical formula, so there is some limitation of temperature and salinities. And temperature, at first, in the ocean, pressure depends on the depth of ocean, and salinity depends on where it is, and temperature depends depth and location. Here is world salinity map, so you can see that at the polar, lower salinity, at the Pacific Ocean, higher salinity, and it's quite different at the world. So, temperature change in the ocean is divided into 3 or 4 layers. Is surface layer and thermocline layer and deep isothermal layer. At the surface layer, wind of surface dips water up and down, so temperature doesn't change. It's recorded surface layer. And in deep ocean, water is the heaviest at the 4 degrees of Celsius. So at the deep ocean, the temperature is about 4 degrees of Celsius. And between surface and deep ocean, there is a layer. The temperature decreases rapidly. We call it thermocline. So, and sound speed also change, but divided by these 3 layers. At the surface, temperature doesn't change, but deeper depth, speed of sound increase. And also in the deep ocean, there's no temperature change, so deeper and deeper, sound of speed higher and higher. But at the thermocline, temperature change rapidly, so sound speed decrease with more deeper with depth. So it divides 3 layers, and it layers. So it makes some speed. Sound is also waves, so refraction occur. Refraction is wave when a wave propagates, it encounters some medium that have a different propagation velocity. The direction is changed. And so Snell's law is describe the relation between angles and velocity like this. So here is some quiz. This is a sound wave, and more deeper in the ocean, sound speed become higher. So in which direction the sound waves go straight or bends? And if it bends, in which direction the sound waves bends? Go straight or bend like this or bend like this? And here is a more higher speed, here is a lower speed, so sound waves go where? Guessing.
I think go offside.
Yeah, the answer is go. I rotate to left side because sound waves tend to bend to lower will to have a lower sound speed. And this is quiz 2, in which direction the sound waves bend, and in the deeper, at the deeper place, the lower temperature and same pressure and salinities. It means here is a more deeper place have a lower sound speed, and here is a sound speed. So it rotates to lower sound speed. It makes a funny, important phenomena. Yeah, it called DSC, deep sound channel. The sounds tend to be focused to a lower sound speed. So here is the lowest area. Here is the area have a lowest sound speed. So sound waves focus here. It tends to here. So at here, sound waves stable, and here sound waves unstable. So if sound source is here, we can hear anything at here because sound waves can't go here. So we call this shadow zone, and under the here shadow zone also is. And within this channel, waves may travel very long distance. So yeah, distance. And lastly, I will introduce some application system, sonar and underwater communication system and acoustic positioning navigation systems. And well, Professor Han already introduced us about sonar, so I'll pass this slide. And as Professor Han said, we use acoustics as a microwave, so microelectric wave. So we use it communication like this, and it also to use to know position. I will show you some video. It explains the principle of acoustic positioning. This one is sound source, and this one is sound sensor. So this calculate of the time and as a calculate time, we can know where it is. So we can know where we is. And also two, and some technology. This technology is to transport sound to image.
Hey guys, Rusty here at Blue Robotics. RV like the Blue ROV2, the Ping 360 ability is only a few feet. It's difficult to get around in the ROV. When you add the scanning sonar to the mix, you get an acoustic image of the surroundings. Here, you can see echoes from the boats, docks, and other features around the ROV. The Ping 360 can see features like this up to 50 meters away. This allows you to navigate the ROV in complicated situations, even when visibility is poor, so you can stay meters away.
As you can see, like here, sonar on ROV detects the where ship is and where ship is and observe the shape of that. And it also use to find enemies. Here is about sources, SOSUS, and
Existed as far back as World War I, but these early systems could only manage detection at distances of a few thousand yards, and even then only under the most favorable conditions. During World War II, sonar technology barely moved past these rudimentary systems, and much anti-submarine surveillance was based on visually identifying the vessels by air as they loitered near the surface to recharge their batteries or bring up their periscopes to target ships. During the 1920s, though, the development of the sonic depth finder was an important first step in developing more advanced and capable sonar systems. Although the various elements of a modern sonar system would not achieve technological maturity or be truly understood until halfway through the Second World War. In 1937, Lay University scientist Maurice Ewing made a critical discovery which would catapult American sonar technology far ahead of its competitors. While doing seismic refraction experiments in water 3 miles deep in the North Atlantic, Ewing used explosive charges placed at different depths to generate sound waves. As Ewing listened to the echoes of the explosions, he discovered that sound signals at very low frequencies could travel great distances with minimal loss. And he postulated that in certain conditions, so-called deep sound channels could exist which would propagate an acoustic signal for hundreds or even thousands of miles. At the same time, the invention and refinement of the bathythermograph by scientists at the Massachusetts Institute of Technology and the Woods Hole Oceanographic Institution made possible for the first time the continuous measurement of ocean temperature at various depths, and more importantly, acoustic signals for as much as thousands of miles. Wasting no time, the Navy immediately authorized a slew of tests for developing these deep sound channels for military use, although at first they would only be used for communications. During the spring of 1944, Ewing supervised a test using the USS Buckley, which steamed away from a receiving ship, dropping explosive charges set to blow at various depths. By determining the pattern of explosions and the depths they occurred at, the Navy hoped to build a system of communication that was impossible to jam and only required a receiving ship to have nothing more than a basic hydrophone. The explosions from the Buckley were clearly discernible until at last the Buckley had to call off the test after reaching a distance of 900 miles and still being clearly heard by the.
This video said acoustics used for find enemies. So acoustics surveillance systems. So, and there are also many other applications. You can find out the appendix of slide. My lecture is over. Thank you.